Hello, my name is Davor Roglic. I'm a product architect at VMware. With me here will also be Rostislav Georgiev, a senior engineer leader at VMware, who will also help answer some questions in the end. We'll be talking about project ELSI that powers our enterprise EDR and dive deeper into some architecture aspects of that project. I'll start talking a little bit about technology dilemma we faced when we were designing our cloud solution, and then I'll move into the architecture. So technology reuse, that's a great thing, right? Where would we be today if we had to rebuild database engine, application server, HTTP from scratch every time? We would be in dark ages of computing, struggling to solve same problem over and over again. And every leap of innovation would come with a large price. Luckily, we are engineers and we learn from our mistakes. We share our knowledge and we don't reinvent the wheel. We'll build a solution that works for a specific problem and then we generalize it. And then we use that as a starting point for something bigger and more difficult. What if that doesn't work? What if the problem you're trying to solve is unusual and hard? For example, build the fastest car in the world. There is no car that would meet that criteria by definition, and there is very little to reuse and simply scale it up, right? So if you're trying to solve such a difficult, extraordinary problem, you have to take some extra risk. So in this presentation, we'll take you to the journey of building something new and something of that kind, and challenges that, and sometimes breakthroughs that we had during this journey. Now, our challenge was far less romantic than building a fastest car. It was instead building the largest EDR solution. Now, what is EDR? EDR stands for Endpoint Detection and Response. It describes technology used in security space, and it records endpoint behavior and responds to malicious activity. As a security analyst, you have to kind of be a detective. You have to follow the clues of unexpected and intentional amongst the very loud noise of normal and expected behavior. And sometimes you just don't know what you're looking for, right? So therefore, EDR solution records everything. It records every process creation, every network connection, file system modification, registry modification, and so forth. And then it brings this to the security analyst on the console with free and ad hoc text search. This way, the analyst can fire a set of arbitrary complex queries to try to zero down through the noise, right, and find potentially the dangerous and the malicious activity. Once they find such activity, they want to be able to automate this, right, and alert the system if they see anything like this in the future. But important thing is it involves a lot of this ad hoc querying that has to be done really fast. And of course, complexity is the scale. As I said, there are tens of millions of endpoints in such a cloud system potentially, and consuming trillions of events per day, tens of petabytes of searchable data. Originally, what I'm showing here is architecture of our original product, which wasn't built for the cloud. Our old product was built on a lot of very, very familiar technologies: Nginx, Tomcat, Solr, Postgres, right? So we built this, and the challenge was mostly building the business logic around it, packaging it, making sure we can deliver it easily, we can troubleshoot it, right? But technologies were well known and well tested. And also, since this product was built for on-prem consumption, it was paid by the customer. Customer will buy the hardware. Customer will maintain it through their IT departments. If customer needs more power or adds more endpoints, they'll buy more hardware, right? So it was kind of a manually scaling, and we were kind of trying to stay as much out of that business as possible, apart from the recommendation. What worked also well in this world is that we found that Solr is actually a really good candidate for our search because it has this very intuitive free text search. And we also realized that storing all the data in this kind of immutable recording fashion really works well for our customers. What didn't work well for this on-prem product was it didn't have really any elastic scaling, right? As on-prem products typically don't have. Sometimes query would be slow and we wouldn't be able to do much about that, right? Except ask customers to buy more hardware and so forth. Data retention was another problem where customer wanted to maybe store data for more than 30 days. Maybe they wanted 60 days, 90 days of data. Only solution is buy more disk space and more hardware. So we knew that this wasn't a good cloud candidate, but we were thinking now, how do we actually bring this to the cloud? How do we build this technology architecture maybe to the cloud? And first we tried it simple. As I said, reuse as much as possible. So let's say, can we just replicate this data in the cloud and have a little cluster for each customer? And very quickly that actually becomes completely unmanageable. We were looking to have thousands and tens of thousands of customers, and it's really hard to imagine having to micromanage and individually scale that many little clusters. And if you try to shove small organizations into shared clusters, you have even more managing problems. And then, what if we take another route? What if we just scale it up and let's build one enormous Solr cluster or Elasticsearch cluster or MongoDB cluster, right? How would that work? That doesn't work either, because you have to have so many nodes in this cluster, thousands or tens of thousands of nodes potentially, right? That it becomes unstable. Yeah, there is so much internode traffic, and none of the technologies is actually built to handle this many petabyte scale of data that needs to be indexed. And finally, we looked at data lake, very popular these days. Everybody builds one. And this approach didn't work mostly for the cost reasons. We tried it, we played with it. In order to get the fast response of the queries that we needed, we would really have to over provision it so much that it would cost at least an order of magnitude more than we wanted to pay for it. And also, the language of data lake is mostly SQL, and SQL is not really very intuitive for our security researchers, right? They really want much more friendly, free text type of search. So we decided to build our own. We adhere to some basic cloud design principles, which probably everybody knows. We also built a set of our own principles we wanted to follow, and mostly around reducing the risk of the entire solution. We want to make sure that we plan for COGS very early, do scale testing very early. We actually started building scale testing before we even started building the solution, right? So it kind of was built in parallel, so we can always validate every step in the way. And given the size that we knew it's going to have, we always wanted to make sure that choreography is favored over orchestration, meaning systems should self-heal, systems should self-scale, right? Rather than having a central kind of a conductor in the middle that controls everything and becomes immediately the weakest link of the system. So architecture, let's talk about that a little more. What we ended up is a system which is streaming architecture, and each of the layers is a separate set of microservices that individually scale horizontally, right? So that was kind of most natural way to think about this. Then streaming in between the layers ensures that there is a low latency of data and high availability. We wanted through that to achieve elasticity, resiliency, and I'll talk some more about the problems there. Important to say is that we still wanted to stick to Solr, right? And more specifically, we were thinking of Lucene, which is underlying engine, and but we didn't want to have a large cluster, right? So we want to kind of separate this large Solr cluster into a lot of individual separate units, and this is why we call it ELSI, stands for Lucene Cloud. First problem we encountered, or we try to solve, as I said, was elasticity. So explain some roots of that problem, right? First of all, our customers have very large variance of data. If you look at the diagram below, you can see those blue dots, and every dot represents a single customer and kind of average amount of traffic that endpoint from this customer sends. And you can see it's all over the place. On the horizontal, you have how many endpoints customer has. On vertical, what is the data volume multiplier compared to the normal average. And you can see that it like varies for sometimes 2 or 3 orders of magnitude, right? So it's a huge, it's very unpredictable. It's hard to tell how much customer will send until we see the customer actually in action, because of a lot of environmental reasons on what might be going on that customer environment. It could be developer systems, it could be point of sale systems, right? Completely different levels of activity. And then on the right, you also see the data volume varies through the day and through the weeks as well, right? We have to account for that. And finally, we want to make sure that data, we can also separate customer data as much as possible, because we wanted to have good story about the privacy. We call it BYOK, meaning bring your own key, where each customer data can be separately encrypted, and customer can actually hold the key of their encryption. So they kind of control the privacy of their data. They can revoke it at any point in time. And we also wanted to have customizable data retention. So every customer can decide for how long to keep their data, which is really very difficult to do in a multi-tenant system unless you really separate data into separate, at least partitions or stores. So how did we do that, right? What was the method for that? So this is high-level view of the approach we took. So you have data coming from the left, from millions of sensors, right? And data comes kind of in a random fashion, right? Because it goes to the gateway, and then it's put into the initial data stream. And this stream is randomly partitioned, right? You cannot really partition it any other way, because otherwise you would have a lot of hot charts. But then you have to, on the other side of that, right, you have to end up with data which is well partitioned per customer. So it goes through kind of entropy reduction stage, right, where we go from this randomness into the partitioned data, and then only then we index the data, and then we have the end up with this per tenant indices, which we can then easily distribute and search. In practice, the way that works is that on the left, you have incoming data, right? Coming, and each data from each tenant has a different volume, right? So depicted here with pink, yellow, and green. And then we measure the traffic as coming in. We kind of have a telemetry about the traffic data for each customer. And based on that, we actually partition the data using Amazon Kinesis streams, which means basically that we will provision more streams, more shards into the stream, which is kind of logical partition of the stream when customer has higher volume of data, and then we will deprovision and reduce number of shards when customer has a lower volume of data. And we will use an explicit hash generation, right, so that we can kind of fill the hash space for the customers that have more data with more partitions, and then reduce it when they don't need it. So Kinesis, for you, some of you probably used it, right? It's not forgiving about how much data you can push into it. So sometimes the challenge is, to make sure that actually this data can flow through the Kinesis, because Kinesis has very strict 1 megabyte per second limit. But that actually, if you can do it, it works in your favor, because anything downstream all of a sudden has very predictable and fixed volume of data. And then downstream from there, we index data, and then after we index it in a bunch of small indices, then we pass it to the next stage, which is merging. The reason we have that is because as the data is high volume and being indexed on one side, it creates a lot of small indices. You cannot really insert data into a large index at very high velocity, because you end up with high churn, and it becomes very expensive to manage. We wanted to basically create very small indices, but then those are not very suitable for searching, and then we merge them into much larger indices later, right? So we have multi-stage processing there to create large and efficient indices for searching. This is how this system actually looks in practice, right? We will you see the ingress for one tenant on the top, and we had at some point very large spike in data. And at the second diagram, you can see that actually it was caused by bringing more endpoints online. What actually happened is these endpoints were active before, but were taken offline for a long time, and they were recording offline, and then all of a sudden they came online and basically flushed their caches into the backend. And then on the bottom, you see how our system actually increased the number of shards. Kind of this effective endpoints depicts the number of of partitions or shards we allocated to this customer, and we responded basically and ingested this data much faster, and then we kind of went to the new equilibrium. The reason the new equilibrium was higher is simply our lazy dumb provisioning logic, which kind of anticipates that data will come from customer at high volume again, right, and keeps it for a few more days. This is something we are tuning, we can adjust. Let's talk about next problem, which is resilience. How do we keep this kind of a multi-stage distributed system resilient to failures? First of all, you know that infrastructure can always and will fail you. There are unexpected failures. On the bottom, you see, for example, just historical graph from one of our days where you can see how many instances actually died at random point in time. And this is pretty normal, right? So system has to be able to handle that, but not only for unexpected, it has to be able to handle it for expected failures like deployments or scaling, right? Scale in, scale out, right? So we had to account for that. And the way we built it was container based, right? So everything is based on Docker containers, and every step of the process is using the local fast storage, because all of these are very disk intensive operations, but it's completely ephemeral and stateless. So at any point in time, if any of these containers goes down, it doesn't lose any data, it doesn't carry any state. All the state is always kept in either Kinesis streams on the upstream side, or when index is completely done, it's immediately written to S3, which is very resilient storage with a lot of nines, right? So we kind of rely on Kinesis and S3, kind of serverless technologies from Amazon, and everything else is really ephemeral and can be recovered automatically. We use a very simple database on top of S3 that will just hold the location of indices for each tenant, so we can actually look it up and quickly recover in case the system goes down. And this was also a nice way to control the retention, because then we can decide, how long we're going to make the index live, right? For how many days, for how many months, simply on S3. And when index expires, we'll just delete it from S3, and deletion will propagate to our registry, and it'll just cause all of the containers to basically remove it from the system. And finally, let's quickly talk about the problem of search. That was kind of self-inflicted problem with our distributed architecture, because what we end up is huge number of indices. The largest customers can have thousands and thousands of indices. So this is like a list of our top, 15 customers, and you see like a different stages of processing, which I mentioned, and at each stage they have different number of these indices, and some have like 5,255 here, for example. And when you do the search, you have to distribute a search request across all of these indices and collect the search results back, right? If you were in Solar Cloud or ElasticSearch, it would do it for you. Since we kind of split this up into containers, we had to do it ourselves, right? So how did we do that? First we tried with kind of maybe simplest brute force approach, and we used kind of in-memory aggregation. You see on the left, basically, a customer issues a search, and then search hits a lot of these indices, right, that are applicable for this tenant, for example. And then the searches are sent through Kinesis, again, as a kind of aggregation stream into our memory aggregator. And then it returns data back. And you can see that this model has actually pretty quick response, right? It's a linear response with number of search results, of course, and cores, but it's relatively quick, right? Data can come anywhere from milliseconds to maybe a few seconds. Unfortunately, if you have a really lot of data, or you ask for a lot of results, this becomes really hard to scale, right? You have to scale it vertically. It's hard to scale it horizontally because of the single aggregation point, right? So you have to kind of scale it vertically and add more hardware and more CPU and RAM, and at some point it's not feasible anymore, right? So we were thinking, like, what do we do now, right? How do we deal with those large data sets? And then we thought of another approach, which is to store all the data to S3 in Parquet format, and then use Amazon Athena to aggregate it for us. So that's the green line here. And you can see actually it can scale almost to infinity. But the problem with it is on the low end, it has overhead. It basically has a couple of second or 4-second overhead regardless of the size of your search. And this is the overhead we didn't want to pay for, right? Or we didn't want customers to experience. So basically, in the end, we took a hybrid approach, best of both worlds. And if there is a small number of results, we'll use memory aggregation. After some point, if search has too many results, we'll switch to Athena. We actually have both of them competing, and whichever comes first, we take the results from there. Give you some stats where we are today, right? We have scaled really a lot in the past 2 years. We've been doing this. We are most proud with our rate of events, which is around 25 million per second, but also our indexed data is over 20 petabytes right now, right? Which is far more than actually we expected that we're going to be able to reach when we started this project. And we are still growing at exponential rate. So that's it. As a summary, to the question, can you build a novel cloud big data technology these days, or should you? Our answer is absolutely. But before you do that, you have to make sure you approach the process understanding your use cases well. You do due diligence, rolling out any existing technologies that may help you. Build it carefully. Try to fail early. Start with cost estimates and tooling for scale testing, and be prepared to own it for a long time. Your team's developers will own it until it reaches maturity, right? You cannot just hand it off to ops and SRE teams. And in the end, you might still fail. But if you succeed, it will make it worthwhile. You will learn a lot and make something that will be difficult to replicate by your competitors. You will get ahead of the curve. All right. Thank you very much. Thank you very much for listening.